Welcome to the new era of video creation with Bayozi8. This is our new series on AI teaching natural language processing. Today, we will discuss the depending parsing. Here are the contents. Dependency parsing is a syntactic analysis task in NLP that focuses on the relationships between words in a sentence. Unlike constituency parsing, which represents sentences as hierarchies of phrases, dependency parsing represents sentences as a tree of word-to-word dependencies. Each word in a sentence is connected to another word, called its head, with a directed edge. This structure is key for understanding how words relate to each other semantically. For instance, in the sentence, "The dog chased the ball," dog is the subject, head of chased, and ball is the object of chased. By mapping out these relationships, dependency parsing helps machines understand sentence structure and the meaning behind it, which is critical for tasks such as machine translation, question answering, and information extraction. A dependency tree is a directed graph, where each node represents a word in the sentence, and the edges represent the syntactic dependency between them. Each word has a directed edge pointing to its head, except for the root word, which has no incoming edge. The tree structure reveals grammatical relationships between words, like which word is the subject of the verb, which is the object, and so on. In a simple sentence like "the cat sleeps," the word "sleeps" is the root of the tree, with "cat" as its subject. The root word is typically the main verb, and the edges show how the other words depend on it. Dependency trees are an essential tool for understanding sentence structure and meaning, especially for tasks like semantic role labeling or machine translation. In dependency parsing, different types of dependencies capture various grammatical roles. Some common types include nominal subject and subject. This is typically the noun or pronoun that acts as the subject of the verb. For example, in the sentence, "The dog barked," dog is the nominal subject of barked. Direct object, dobj. This word is the noun or pronoun that receives the action of the verb, like ball in "the dog chased the ball." Modifier dependencies. These include adjectives, adverbs, and determiners. For instance, in "The big dog barked loudly," big is a modifier of dog, and loudly is a modifier of barked. Prepositional phrase, prep. This describes the relationship between a verb and a preposition, like "in the park," in "The dog barked in the park," where park is the object of the preposition in. These dependency types help define the role each word plays in the sentence and provide a detailed syntactic analysis. Dependency parsing is central to many advanced NLP tasks because it provides deep insights into the syntactic structure of sentences. By understanding the relationships between words, we can derive meaning more accurately. For example, in machine translation, knowing which words depend on each other allows systems to maintain the correct word order when translating between languages with different syntactic structures. In question answering systems, dependency parsing helps to identify the key parts of the question and map them to the relevant parts of a passage. In information extraction, dependency parsing helps extract relations and entities more effectively by understanding how words are related in the context of a sentence. Additionally, dependency parsing aids in handling syntactic ambiguity, such as distinguishing between different interpretations of a sentence based on word dependencies. Dependency parsing and constituency parsing are two fundamental approaches to syntactic analysis, each with distinct advantages. Dependency parsing focuses on word-to-word relationships, representing sentences as a tree of words connected by directed edges. Each word is linked to its syntactic head, making the relationships between words explicit. Constituency parsing, on the other hand, represents sentences as hierarchical trees, where words are grouped into phrases, e.g., noun phrases, verb phrases. This type of parsing is typically more abstract, as it focuses on phrase structure rather than individual word dependencies. While constituency parsing captures higher-level structures, dependency parsing provides a more detailed and flexible view of how individual words relate to each other. There are several parsing algorithms used to construct dependency trees. Shift-reduce parsing. This is one of the most common algorithms for dependency parsing. It incrementally builds the tree by shifting words onto a stack or reducing subtrees to smaller components. Early parser. The early algorithm is used for parsing ambiguous grammars and is known for its efficiency in handling various sentence structures. It can handle both context-free and dependency grammars. Transition-based parsing. This approach uses a sequence of transitions, actions, to build the tree, such as shifting a word onto a stack or reducing a subtree. It is efficient and suitable for online parsing. Graph-based parsing. This models dependency parsing as an optimization problem over a graph, where edges represent possible dependencies, and the best parsing is obtained by finding the optimal graph structure. These algorithms differ in their efficiency, accuracy, and ability to handle ambiguous sentences, and each has its place in different NLP systems. Training high-quality dependency parsers requires annotated data, specifically dependency trees labeled with the correct word dependencies. Some well-known annotated corpora include universal dependencies, UD, a cross-linguistic initiative to create a universal framework for dependency parsing with consistent annotations across multiple languages. Penn Treebank, primarily used for constituency parsing, but also contains dependency annotations for training models. The quality of annotations is critical. Errors in the labeled data can significantly affect the performance of the trained parser. In practice, many dependency parsers leverage pre-trained models to improve their accuracy, especially for languages with limited training data. Transition-based parsing is a technique where the parser builds the dependency tree incrementally by performing a series of actions. These actions include shift, move a word onto a stack, reduce, remove a word from the stack and create a subtree, arc, create a dependency edge between two words. This approach is especially useful in online learning, where the parser processes sentences in real time and can be adapted as it processes more data. Transition-based parsers are fast and efficient, making them suitable for large-scale applications like speech recognition and real-time language translation. Graph-based parsing represents the sentence as a graph where nodes are words and edges are potential dependencies. The task then becomes finding the maximum spanning tree of the graph, where the tree structure captures the best set of dependencies for the sentence. This approach is particularly useful for unsupervised parsing, where no labeled data is available. The optimization approach also makes it suitable for large-scale models, such as those used in web-scale applications like information retrieval and knowledge extraction. Evaluating dependency parsers involves several metrics. Unlabeled attachment score, UAS, measures the percentage of words in a sentence that have the correct head, regardless of the dependency label. Labeled attachment score, LAS, more stringent, as it also considers whether the correct dependency label is assigned to the edge between the head and the dependent. Speed and efficiency. In real-time applications, such as machine translation or speech-to-text systems, the speed of the parser is as important as its accuracy. Accuracy versus complexity. There is often a trade-off between the complexity of the parsing model and its performance. More complex models tend to be more accurate but also slower and require more computational resources. Dependency parsing plays a crucial role in various NLP tasks. Machine translation. Dependency parsing helps maintain grammatical correctness and syntactic relationships between words when translating between languages with different word orders. Information extraction. By analyzing word dependencies, dependency parsers can better identify named entities and relations in text, which is vital for tasks like automatic summarization and data mining. Question answering. Dependency parsing can help match questions with the right contextual passages, identifying the relevant relationships between words in both the question and the passage. Sentiment analysis. Understanding the dependencies between words helps detect sentiment at both the word and phrase level, making the analysis more accurate. Dependency parsing faces several challenges. Ambiguity. Many sentences can be parsed in multiple ways. For example, I saw the man with the telescope can have different dependency structures depending on whether with the telescope modifies man or saw. Cross-lingual parsing. Different languages have varying syntactic structures. For example, in languages like German, word order is more flexible than in English, making parsing more difficult. 3. Data scarcity. High quality. Annotated data is needed to train parsers, but for many languages, such data is scarce or unavailable. 4. Long-range dependencies. Handling relationships between words that are far apart in the sentence remains challenging, especially when dealing with long sentences. Looking ahead, the field of dependency parsing is likely to evolve in several key ways. Handling ambiguity. Research will continue to improve techniques for resolving syntactic ambiguity in sentences, making parsers more robust in real-world applications. Multilingual parsing. As NLP becomes more global, dependency parsers will be extended to handle a wider range of languages, each with its own syntactic structures. Deep learning integration. With the rise of deep learning, there is increasing interest in combining neural networks with traditional parsing methods for higher accuracy and efficiency. Real-time parsing. Advances in real-time dependency. Parsing will be critical for applications like speech recognition, where immediate processing is required. In conclusion, dependency parsing is a foundational technique in NLP that provides insights into the syntactic relationships between words in a sentence. It is crucial for tasks like machine translation, information extraction, and question answering. The various parsing algorithms, such as transition-based and graph-based, offer different trade-offs in terms of speed and accuracy. As NLP continues to evolve, we expect to see improvements in deep learning-based parsers, more efficient handling of ambiguity, and multilingual models. Thank you for your attention, and I'm happy to take any questions.